cavitation, flashing, noise, and erosion. Every design engineer must anticipate. This module addresses the destructive side of control valve service, where fluid energy, phase change, and velocity concentrate inside the valve. These phenomena are not edge cases. They are predictable outcomes of pressure drop, recovery, and geometry. When not anticipated at design stage, they manifest as noise complaints, unstable control, rapid trim loss, and unplanned shutdowns. When anticipated correctly, they are managed, not eliminated by design. Cavitation mechanics. Image cavitation occurs when local static pressure inside the valve drops below the liquid vapor pressure, forming vapor bubbles that collapse violently as pressure recovers downstream. The collapse releases microjets and shock waves that attack metal surfaces. Pressure recovery factor. Pressure recovery describes how much pressure a valve regains after the vena contracta. Key concepts. High pressure recovery valves regain pressure rapidly. Rapid recovery increases the likelihood of cavitation collapse. Valve geometry, cages, ports, passages governs recovery. Design implication. Two valves with the same CV can have very different cavitation behavior. High recovery designs require special trims at high delta P. Ignoring recovery is the fastest way to design cavitation into a system. Half damage patterns. Cavitation damage is directional and localized, not uniform. Typical patterns: pitting downstream of the seat or cage, horseshoe-shaped erosion marks, surface work hardening followed by cracking, progressive noise increase before catastrophic failure. Control impact: changing trim geometry alters valve gain. Control becomes unstable long before mechanical failure is obvious. Cavitation is both a mechanical failure mode and a control degradation mechanism. Design prevention strategies. Cavitation cannot always be eliminated, but it can be controlled. Primary strategies: reduce pressure drop per stage, shift energy dissipation away from solid surfaces, use multi-stage or anti-cavitation trims, select lower recovery valve geometries, increase downstream pressure when possible. Effective cavitation design focuses on where bubbles collapse, not just whether they form. Flashing services. Image flashing occurs when downstream pressure falls below vapor pressure permanently, so vapor does not collapse. It continues downstream as a two-phase mixture. Trim erosion. Unlike cavitation, flashing causes continuous high-velocity particle erosion. Characteristics: material loss rather than pitting, directional wear aligned with flow, rapid thinning of trim edges, accelerated body damage in severe cases. Control consequence: CV increases over time, valve gain rises unpredictably, loop tuning degrades progressively. Flashing damage is quieter than cavitation, but often more destructive. Material selection. Material choice becomes critical in flashing service. Common strategies: hardened alloys, tungsten carbide coatings, ceramic or composite trims, sacrificial components designed for replacement. Material selection must balance erosion resistance, manufacturability, cost, maintainability. Incorrect material choice guarantees repeated failures regardless of trim design. Velocity management. Velocity, not pressure, is the dominant variable in flashing erosion. Design approaches: larger valve sizes to reduce velocity, diffusers or expanders downstream, multi-path trims to spread flow. Avoid sharp turns immediately downstream. If velocity is not managed, erosion becomes inevitable. Noise generation and abatement. Image noise is not merely an environmental concern. It is an indicator of extreme energy dissipation that often precedes mechanical failure. Aerodynamic versus hydrodynamic noise. Aerodynamic noise occurs in gas and steam services caused by shock waves and turbulent jets, increases sharply near choked flow. Hydrodynamic noise occurs in liquid services, closely linked to cavitation and flashing, often broadband and structure-borne. Both types indicate high internal velocities, contribute to fatigue and vibration, degrade instrumentation and piping integrity. Multi-stage trims. Multi-stage trims are the most effective noise control strategy. How they work: divide pressure drop across multiple restrictions, reduce jet velocity at each stage, prevent shockwave formation, shift energy dissipation internally and uniformly. Design trade-offs: higher cost, increased size, greater complexity, significantly improved reliability. Multi-stage trims are preventive investments, not luxury options. Regulatory noise limits. Industrial noise is governed by occupational and environmental limits. Design implications. Noise must be predicted during sizing, not after installation. Valve selection may be driven by acoustic limits rather than flow. Oversizing to reduce noise can reintroduce control problems. Good design balances. Noise compliance, control authority, mechanical integrity. Noise problems discovered after commissioning are rarely solved cheaply. Cavitation, flashing, noise, and erosion are not surprises. They are physics expressing itself inside a valve. Design engineers who anticipate these modes treat control valves as energy management devices, not just flow regulators. When these phenomena are engineered consciously, valves live long, control remains stable, and failures become rare rather than routine. Materials, packing, and special services. Designing for temperature, corrosion, and safety. This module addresses a truth every experienced design engineer eventually learns the hard way. Most control valve failures are not sizing failures, they are materials failures. Valves live at the intersection of pressure, temperature, chemistry, and motion. When materials and sealing systems are mismatched to service conditions, control quality degrades first, and mechanical failure follows shortly after. Good materials engineering makes valves boring. Bad materials engineering makes them unforgettable. I-body and trim materials image. Material selection begins with the assumption that the valve will see worst-case conditions, not normal ones. Carbon steel, stainless steel, and alloys. Carbon steel, economical and widely available, suitable for moderate temperature and non-corrosive services. Limited resistance to corrosion and thermal cycling. Used where fluids are clean and stable, temperature excursions are predictable, cost sensitivity is high. Stainless steel, improved corrosion resistance, better performance at elevated temperatures, more tolerant of process variability. Used where chemical compatibility matters, temperature swings are frequent, product contamination must be avoided. Alloy steels and exotic alloys, designed for extreme environments, resist corrosion, hydrogen damage, and high temperature creep, significantly higher cost and lead time. Used where failure is unacceptable, fluids are aggressive, temperatures or pressures exceed conventional limits. Material selection is not about corrosion tables alone, it is about long-term mechanical stability under cyclic stress. Hard facing and erosion resistance. In many services, base material is insufficient to survive throttling. Hard-facing strategies, stillite or cobalt-based overlays, tungsten carbide coatings, ceramic inserts. Purpose: increase surface hardness, reduce erosion and galling, preserve trim geometry over time. Trade-offs: increased cost, more complex manufacturing, potential brittleness if misapplied. Hard-facing should be applied selectively, where velocity, cavitation, or flashing demand it. Packing systems. Image packing is the most underestimated control valve component. It directly affects emissions, friction, responsiveness, and maintenance frequency. Graphite versus PTFE. Graphite packing, excellent high temperature capability, chemically inert, stable over wide temperature ranges. Limitations: higher friction, increased stem wear, greater deadband risk. PTFE packing, low friction, excellent chemical resistance, good for low to moderate temperatures. Limitations: temperature sensitive, cold flow under sustained load, limited fire resistance. Packing choice directly influences control precision, not just leakage. Low emission packing. Environmental and safety regulations have pushed packing design into a critical role. Low emission systems feature multiple sealing rings, live loading springs, controlled compression. Benefits: reduced fugitive emissions, stable sealing over time, less frequent retightening. Trade-off: increased friction, higher actuator force requirement. Design engineers must account for packing friction early. Retroactively correcting actuator sizing is rarely feasible. Friction versus sealing trade-off. There is no free lunch. Tighter packing, better sealing, worse control. Looser packing, better control, higher emissions. Good design balances, regulatory compliance, control performance, maintenance philosophy. Excessive focus on zero leakage often destroys controllability, which then causes process instability and increased wear elsewhere. Special applications. Image. Some services push valves beyond conventional design assumptions. Cryogenic valves. Cryogenic service introduces extreme thermal gradients, design challenges, material embrittlement, seal contraction, ice formation. Design solutions, extended bonnets to isolate packing, austenitic stainless steels, special stem and seal designs. Control implication, slow thermal response, increased friction variability, careful positioner tuning required. Cryogenic valves are as much thermal systems as flow devices. High temperature service. High temperatures attack both strength and geometry. Challenges, creep deformation, oxidation, packing degradation. Design strategies, high temperature alloys, metal-to-metal seating, extended bonnets, reduced stroke speeds. At high temperatures, dimensional stability matters more than initial strength. Nuclear and safety-critical valves. In safety-critical services, control valves become part of the protection system, not just regulation. Key requirements: qualified materials and manufacturing, redundant sealing, proven fail-safe action, extensive documentation and traceability. Design philosophy: predictability over optimization, conservatism over efficiency, proven designs over innovation. In these applications, the valve must perform once, under worst conditions, without hesitation. Materials, packing, and special service design define whether a control valve survives its environment or becomes its first casualty. Engineers who treat material selection as a control variable, not a procurement detail, design valves that age gracefully, control reliably, and fail rarely.